Deep learning and neural networks have been responsible for recent breakthroughs in problems like computer vision, machine translation, and time series prediction. Did you know that we can combine such neural networks with reinforcement learning algorithms to create models that have superhuman abilities? Hello, this is Rishabh Jain from RQ Productions, and today I will be talking about reinforcement learning. Reinforcement learning refers to goal-oriented algorithms, which learn how to attain a complex objective, for example, maximizing the points won in a game over many individual moves. They can start from a blank slate, and under the right conditions, they can achieve human-like or even superhuman performance. Like a child incentivized by both the negative, yelling, and the positive, like candy. Such reinforcement algorithms are penalized when they make the wrong decisions and are rewarded when they make the right ones. Reinforcement algorithms that use deep learning have the potential to beat world champions at the game of Go, as well as human experts playing numerous Atari video games. While that may sound trivial, it's a vast improvement over their previous accomplishments within the last few years, and the state of the art is progressing rapidly as technology and supercomputing improves. Reinforcement learning solves the difficult problem of correlating immediate actions with the delayed returns that they might produce. Like humans, reinforcement learning algorithms sometimes have to wait a while to see the fruit of their decisions, like a cause and effect. They operate in a delayed return environment where it can be difficult to understand which action leads to which outcome over many time and many steps. This has proved to excel at scenarios and games, for example, chess, where the results of an action, for example moving a piece, may not unfold entirely until a few moves later. This helps the algorithm not make immediate guesses about something that may prove to later be untrue. Reinforcement learning can be understood using the concepts of agents, environments, states, actions, and rewards. I will be defining a few of the most important ones here. Agent. An agent takes actions, for example, a drone making a delivery, or Super Mario navigating a video game. The algorithm is the agent, and in real life, the agent would be you. Action. An action is the set of all possible moves that the agent can make. An action is pretty much self-explanatory, but it should be noted that agents choose among a list of possible actions. In video games, the list might include running right or left, jumping high or low, crouching, or standing still. And when handling aerial drones like we talked about in the previous example of the agent, alternatives would include many different velocities of the drone and accelerations in 3D space. The action list would usually be determined by you if you're inputting it into an algorithm. Discount factor. The discount factor is multiplied by future rewards as discovered by the agent in order to dampen the reward's effect on the agent's choice of action. Well, why would we want to do that? Well, it is designed to make future rewards worth less than immediate rewards in some cases. Sometimes it enforces a kind of short-term hedonism in the agent. Often expressed with the lowercase Greek letter gamma, if gamma is 0.8 and there's a reward of 10 points after 3 time steps, the value of that reward would naturally be 0.8 to the power of 3 times 10. But if we implement a discount factor, for example 1, that would make future rewards worth just as much as immediate rewards. Reward. Again, this one is kind of self-explanatory. A reward is the feedback by which we measure the success or failure of an agent's actions. For example, in a video game, when Mario touches a coin, he wins points. From the given state, an agent sends outputs in the form of actions to the environment, and the environment returns the agent's new state, which resulted from acting on the previous state, as well as rewards, if there are any. Rewards can be immediate or delayed. They effectively evaluate the agent's action. From all of these, thanks to skymindai, we also have a feedback loop taking each of these actions. The agent takes an action in the world of the agent, resulting in the state changing and a reward being produced. This could be Mario jumping and hitting a brown block, changing the block's color and resulting in him receiving a coin. Over time, our model could learn that jumping to change a block's color is good and we will get rewards from it. To conclude, reinforcement learning tells us that the agent's actions change the environment. The agent then observes the changes in the environment and then acts again, receiving more observations and information in the form of rewards. The agent learns with practice and how to get more rewards. The algorithm is extremely powerful and allows us to create models in conjunction with neural networks like AlphaGo and Deepmind, which have the capability to beat world-class humans at games and other activities. I'd like to thank you for watching. Consider liking and subscribing so you can watch the rest of our AI videos and learn a lot about artificial intelligence. Thanks for watching.